can have the recording on Blackboard. Okay. All right. The topic for today is cyclic codes, and in the last lecture, I started with a discussion on cyclic codes. Okay, I gave you a brief introduction about what is the cyclic codes, and also we talked about the polynomial representation of binary sequences. Right, we did that in the last lecture. Let me quickly recap that. Basically, we want to represent bits, binary sequences as polynomials. Okay, and if you remember, in the last lecture I gave an example of 4 bits. Okay, so with 4 bits you have 16 possible combinations starting from 0000 up to 1111, and we want to represent these as polynomials. Basically it's giving a weight in terms of the powers. Okay, so the rightmost number is d power 0, d power 1, d power 2, d power 3, right? So it's like the ones, tens, hundreds, and thousand. Right? When you write a number, it's you ones position, tens position, hundreds position, right? So ones means d power 0, d power 1 is it's like 10, d square is 10 square, 100, right, and so on. So we start with the rightmost with the power of 0 and then move inwards towards the left by increasing the power by 1 each time, right? So d power 0, d power 1, d power 2, d power 3. And then for the binary sequence, we see which position has a 1, and whichever position has a 1, that position will have a value. If there is a 0, that position will have no value. That means that that element will not appear. So for example, in 0000, all the 4 numbers are 0, so the polynomial is simply 0. For 0001, only the position for d power 0, d power 0 is basically 1, right? So only that position is 1, so you get it as 1. In 0010, only the position for d power 1 is having a 1, so d power 1 is d, so the polynomial corresponding to that is d. For 0011, you have d power 1 and d power 0, both have a 1 under them, so d power 1 is d and d power 0 is 1, so d plus 1 becomes the polynomial corresponding to this binary sequence. And similarly, you can find the binary sequence for all the other message sequences. And the last two, if you see 1110, there is a term, there is a 1 under d power 3, so you have d power 3. There is a 1 under d square, so you have d square, and there is a 1 under d power 1, so you have d. So the polynomial corresponding to 1100 is 1110 is d cube plus d square plus d. Similarly, for the last one, which has all ones, all the powers are present. Yani d power 3, d power 2, d power 1, and d power 0. So all of them are present. Okay, so we are basically representing the binary sequence as a polynomial because we are going to use these polynomials to multiply things, and it becomes like polynomial multiplication. Okay, and the first observation we make here is that when the length of the binary sequence is 4, the highest power that you have is 3. When the length is 5, it will be 4, the highest power, right? So the highest power will be 1 less than the length of the sequence itself. Okay, so when the sequence is 4 bits long, the highest power is d power 3. 4 minus 1 is 3. So in general, when we have messages of length k, because we are going to talk about codes as nk codes, right? So the message length is k. So with a message length of k, the corresponding polynomial will have a degree of k minus 1, and that means the highest power that the polynomial can have is k minus 1. So if you notice all these polynomials starting from 0000 to 1111, in all of them the highest power is k minus 1, which is uh, 4 minus 1, and that is 3. So there won't be any term which has a power more than 3. Okay, and we represent the message polynomial by the letter I because it represents the information, right? The information that we are trying to code. So the message polynomial, we denote that as I of d, and we represent them as the polynomial. So for each of them, I of d for the first one is simply 0, I of d for the second one is 1, I of d for the third message is d, I of d for the fourth message is d plus 1, and so on and so forth. Okay, so we call or we denote the message polynomial or the information polynomial by the term I of d. And then we are interested in finding the code word polynomials. We'll call the code word polynomial by the letter C. So C of d is the code word polynomial. And how do we get the code word polynomial? We multiply the message polynomial I of d with another polynomial of d, which is called as the generator polynomial. The generator polynomial, like we have the generator matrix in the 7-4 Hamming code and the 6-3 linear code, similarly, for the cyclic codes, we are going to have the generator polynomial, which we call as g of d. And how do we get the generator polynomial? All of that we'll see in the next page. But before we move further, I want to highlight some properties of the cyclic code. The first property of the cyclic code is that it's a linear code, right? Linear code means if you add any two code words from this set of codes, then the result will also be from the same set. So addition of any two code words will produce an answer which lies within the set. Okay, we will prove that once we generate all the code words for the 16 messages. We will prove that in a little while. And the second property is that it's a cyclic code. That means if we shift the code word cyclically to the left or to the right, the shifted version will also be a code word. Yeah, the scan picture is not clear, I know. Focus on what is written now. Okay, my handwriting, focus on this. You will see the scan picture. I will upload the scan picture on the lecture section so you can read it there. So what is in the scan picture, I'm explaining that verbally. Okay, so and also it's written here also. The important points are written on the right side. Okay, so focus on these things. So now we are talking about the cyclic code. That means a cyclic shift of them will produce another code word from the same set. That is why we call them as cyclic codes. We'll see the examples of that. Okay, in the next pages we will see the examples of of this set of codes, and we'll prove that when we cyclically shift each code word, it produces an answer which is from the same set. Okay, but for now we want to focus on how do we get the generator polynomial g of d. Okay, let's look at that. Where is my sharing? No sharing. Okay, let's go to the next page now. Okay, so if you want to produce an NK code, okay, N is the block length, K is the number of message bits. So the code word polynomial, as we have seen earlier, is going to be having a degree of K minus 1. Sorry, the message polynomial K minus 1. And the code word polynomial, because the length of the code word is going to be N, so the code word polynomial is going to have a degree of N minus 1. And when you multiply the message polynomial with the generator polynomial, you will get the code word polynomial. So therefore, the generator polynomial is going to have a degree of 3. The highest power, or the generator polynomial will be having a power of n minus k. So when you multiply a polynomial of power n minus k with a polynomial of k minus 1, you will get a polynomial of n minus 1, right? So the degree of the generator polynomial is going to be n minus k. And the second thing is the generator polynomial should be a factor of another polynomial which is d power n plus 1. So for example, if we are going to produce a 7-4 cyclic code, like we had a 7-4 Hamming code, we can also have a 7-4 cyclic code. So n is 7, k is 4. In this case, the generator polynomial g of d must be a factor of d power 7 plus 1, because n here is 7. So a factor of something means it divides that polynomial without any remainder. Okay, and the generator polynomial must have a degree of n minus k. In this case, 7 minus 4 is 3. So To produce a 7-4 cyclic code, we need to create, or we need to find a generator polynomial which is a factor of d power 7 plus 1, and it has a power d power 3, right? A degree of 3. Such a polynomial can be used as the generator polynomial for producing the cyclic code. So we are going to find the factors of d power 7 plus 1, and then we will choose the factor which has a degree 3 to be used as our generator polynomial. Okay, let's see that in the next page. Here we go. So when you factorize d power 7 plus 1, okay, you just basically divide it by d plus 1 and c, okay, and break it down. So it's like if I give you a number 20, the factor of 20, 5 and 4 are both factors of 25 into 4 gives you 20, right? So the factors of anything are all the numbers or all the polynomials which have a lower power than that, which divide the bigger polynomial without any remainder. So d power 7 plus 1, so 7 is the higher power, so all the factors will have a power which is less than 7, and when you divide d power 7 plus 1 by any of these three factors, it will give you a remainder of 0. That is why they are called as factors. Okay, now to be used as a generator polynomial for an nk code, or in this case for a 7-4 code, the generator polynomial must have a degree of 3. And when you factorize this d power 7 plus 1, you have two polynomials which have degree 3. So you have the first one here, d power 3 plus d plus 1. So that is also of degree 3. And the second one here, d power 3 plus d square plus 1, that is also of degree 3. So that means both of these qualify as generator polynomials. We can use the first one, d power 3 plus d plus 1, or the second one, d power 3 plus d square plus 1. Both of them can be used as our generator polynomials to produce the code words. Okay? So I'm going to start off with the first one here, and the choice of the generator polynomial has an effect on the properties of the code word in terms of their error detection and error correction capabilities. And which generator polynomial is good and which is not so good, that you need to generate the codes and see how they perform. Okay, there is no simple mechanism to know that this generator polynomial is going to be good or this is going to be bad, or if you have multiple of them, how to choose which one, right? You'll have to try all of them and choose the one which gives the best results. So let us focus on the encoding. We are not going to consider the results in this particular course. We just want to focus on the procedures, how to do the encoding and how to do the decoding. So let us start with choosing d cube plus d plus 1 as our generator polynomial. So we have g of d is d cube plus d plus 1. And to produce the code word, we need to multiply the message polynomial with the generator polynomial. So we are going to choose one of the message polynomials. For example, for the message 0011, the corresponding message polynomial is d plus 1. Okay, if you let me quickly go back to the previous page, if I can show you in the first page. So for 0011, if you see here, the polynomial for the message is d plus 1, right? So we are going to choose that message, d plus 1, and then multiply it with this generator polynomial, d cube plus d plus 1, and that should give us our code word polynomial, which we denote as c of d. So c of d is obtained by multiplying this message polynomial, which is d plus 1, with the generator polynomial, and when you multiply this you get these terms. Okay, that's a straightforward multiplication. D into d cube is d power 4, d into d is d square, d into 1 is d, plus 1 into d cube is d cube, plus 1 into d is d, plus 1 into 1 is 1. Now the important thing that you need to remember here is that these additions that are there are XOR operations or modulo 2 additions, right? These additions are modulo 2. That means 1 plus 1 becomes 2, and 2 modulo 2 is 0, right? So any term that appears 2 times or 4 times or 6 times, they'll all cancel out. Every pair of occurrences will be cancelled out. So if you notice here, the term d power 1 appears twice, so we have cancelled that out. So d power 1, d power 1. So because it's modulo 2 addition or XOR operation, so 1 plus 1 will become 2, right? 1d plus 1d, that's 2d, right? So if it's an even number, it becomes 0. So anything that appears twice or 4 times or 6 times, all of them will cancel out. So every pair gets cancelled out. So in this case, we have only one pair, which is d, which occurs 2 times. So once we cancelled out, the remaining terms are nothing but the code word polynomial terms. So we have for the code word d power 4, d cube, d square, and 1. So we write it from the highest power, and then we go down towards the lower powers. So the highest power is 4, then the next highest is 3, then the next highest is 2, and then the next highest is d power 0, that is 1, right? And then because we are doing a 7-4 code, that means the code word polynomial represents a vector of 7 bits long. So the powers will go from d power 0 at the rightmost position to d power 6, that is d power n minus 1. N in this case is 7. 7 minus 1 becomes 6. So the degree, the highest degree that the code word polynomial can have is d power 6. So once you write these elements, you just need to fill the places with ones wherever that power exists in the code word polynomial. Okay. So if you notice in the code word polynomial, there is no d power 6. So for d power 6, you put 0. There is no d power 5, so you put it 0. D power 4, it is present, so you put it a 1. D power 3 is also there, so you put a 1 under d power 3. D square is also 1, so you put a 1. There is no d here, so d power 1 becomes 0. And d power 0 is basically 1, the constant term, and that is a 1. It's present, so we put a 1. So effectively, we started with the message 0011, and then when you code it, what you get is 0011101. Okay, and that is the code word corresponding to the message 0011. Now it appears that this is systematic. Systematic means the message bits appear as they are in the code word, right? So 0011 is the message, and the code word has 0011. So it appears to be systematic, but it is not systematic because only for the first few code words we get such a result. After the fourth code word, you will see that if you see in this scanned paper, you will see that the message and the code word, the message does not appear in the code word as it is. For example, the fifth one, 0100, the code word starts with 0101, so the message does not appear as it is. So even for the fifth one, the message is 0101, and the code word here starts with 0100. For the seventh one, it is 0110, and here it is 0111. So you see that uh, except for the first four code words, all the other words are not systematics. Okay, so if it's systematic, it means all the code words will have the message as it is in the front part of the code word. But in this case, only the first four by chance they are there, but all the others are not. So therefore, the cyclic code that we are dealing here is not a systematic code. Okay, only the first four code words happen to appear systematic. Okay, but to be called truly systematic, all the code words must be having the messages in front without being altered, and that is not the case starting from the fifth message. So therefore the 7-4 cyclic code is not a systematic code. So how do we produce the code word? We simply multiply the message polynomial with the generator polynomial, and we get the code word polynomial, and finally we map the code word polynomial back to the binary sequence, and we get our code word polynomial, the code word bits. Okay, right. Let's look at some properties of these cyclic codes. Okay, I have done the calculations for all the 16 messages. So you will see in the scan sheet, I will upload it on Blackboard for you guys. So it will be very clear for you. And the procedure is very straightforward. You just multiply the message polynomial with the generator polynomial, you get the code word polynomial, and you convert the polynomial of the code word to the code word bits. And you have all the 16 code words shown here, and their calculations are also shown on the next page. Okay, so the next page here, it shows you the calculations for all the 16 messages. Okay, the corresponding message polynomial multiplied with the generator polynomial, and you get the code word polynomial, and the code word bits are shown here. Now I'm not going to repeat those calculations for all the 16 messages. You can do it yourself. I've done one illustration for you. But what I want to focus now is the two properties of the cyclic codes. The first property that we saw in the very first page is that the cyclic codes are linear codes. That means if we add any two code words, it should produce the answer which lies within the set of code words. So for example, we will take two code words. Okay, if you go here, there are 16 code words. There are 16 code words on the right side column here. So we will take two of them. For example, we will take second code word 0001 011 and the third code word 0010 110 and add them together. The result should be one of these 16. When you add two code words, the result should be from the same set of code words. So that is when you can call it as linear. So let us add the second and the third and see what we get. So when you add second code word with the third code word 0001 011 plus 0010 110, and remember this addition here is modulo 2 addition. That means it's an XOR operation. So when you add them, the result that you get is this: wherever the bits are same in both the rows, the answer is 0. Wherever they are different, it becomes 1. That is the XOR operation, right? So the result that you get is 0011 101. And go back to the table and see 0011 is also within that set. So let's see here, 0011 101. So that means when you add the second code word and the third code word, what you get is the fourth code word. Okay, it can be any of them, right? Similarly, if you add any two of these code words from this set, you will get an answer which is within the same set of 16 code words. So that is why we call them as linear codes. Okay, cyclic codes, the 7/4 cyclic code that we are talking about now is a linear code. So that means the sum of any two code words modulo 2 will be another code word within the same set. And I have given an example by adding the second and the third code word, and the result happens to be the fourth code word. It could be any of them, right? So that's the first property of cyclic codes, that they are linear. The second property of cyclic codes is that they are cyclic. Means a cyclic shift of any code word will result in an answer which is also a code word from that same set. So again, let me take the second code word 0001 011 and shift it in the counterclockwise direction. That means a right shift. Okay, that means the rightmost bit goes out and comes as the leftmost bit, and all the other bits move to the right by 1 position. So this one, the rightmost one, goes out and comes as the first bit. So the rightmost one rotates out and comes back to the leftmost position. So we have a 1 here, and all the other positions shift right by 1 position. So you see the first bit becomes the second bit, the second becomes the third becomes the fourth becomes the fifth becomes the sixth becomes the seventh, and the seventh goes out and becomes the first. So when we cyclically shift the second code word, we get the answer 1000101. And if you notice from the previous table, this is also a code word 1000101. So let's go back to that. The second code word is this 0001 011, and when you shift it, you get 1000101, which is this one. Okay, so you see here I'm just highlighting the pointer. So when you cyclically shift the second code word to the right, then you get 1000101, which is this code word, right? 1000101, is that correct? Yes. So a cyclic shift of any code word, whether the cyclic shift is to the right or to the left, it will produce an answer from the same set. That is why we call them as cyclic codes. So we've taken the second code word and did a right shift. Similarly, we will do a left shift and see what we get. So when we do a left shift of second code word, that means the leftmost bit goes out and comes as the rightmost bit, and everything else gets shifted left to one by one position. So when you shift this to the left by one bit, what do you get? 0010110. So let's look back at the table. 0010110. So the second code word, when it is shifted to the left, gives you the third code word. When it is shifted to the right, gives you the 1000101, this particular code word, which is 1 2 3 4, the fifth row from the bottom, right? So the fifth one from the bottom, that's what you get. So any cyclic shift of any of these 16 code words will produce another code word. So cyclic shifts will result in an answer which falls within the same 16 code words, and that is an interesting property of cyclic codes. Again, I can't cover uh, the performance details of this property, but you should know what it means. Okay, what is the meaning of a cyclic shift, and what do we mean by cyclic codes? Okay, so to summarize now, the cyclic codes are linear codes. That means when you add any two code words, you get another code word, and a cyclic shift of any code word also produces another code word from the same set. Okay, so that's the properties and the generation of the cyclic codes. So how do you produce the cyclic code? You find a generator matrix, generator polynomial of power n minus k, and multiply the message polynomial with the generator polynomial, and that will give you the code word polynomial, and from the code word polynomial you get the code words, and the code words will have the property of being linear and cyclic. Right, that's the encoding part, how to produce the code words. Okay, now we want to look into the decoding part. From the code word, I want to get back the message, and clearly, because they are not systematic codes, you can't just get back the message directly from the first k bits, because they are no longer the same 4 bits, except for the first 4. It happens to be by chance for this case, but all the other code words, if you see, the message bits are jumbled up. They are no longer the same, and they are not systematic in the code word. So therefore, what is the procedure to find the message bits back from the code word bits, from the code word polynomial? So for that, we want to find what is called as the parity check polynomial. Again, like in the Hamming codes, we had the generator matrix and the parity matrix, the parity check matrix, H matrix. Here we call it as the generator polynomial and the parity check polynomial. So the parity check polynomial can be obtained from the other factors of the the main polynomial of d power n, right? We started with d power 7 plus 1, and we factorized this, and we got the 3 polynomials. Out of the 3, we chose one of them of power n minus k as our generator polynomial. The remaining terms will become your parity check polynomial, because when you multiply the generator polynomial with the parity check polynomial, that should give back your original d power 7 plus 1 or d power n plus 1 polynomial, right? In this case, because we are dealing with the 7-4 code, it's d power 7 plus 1. So we have taken this as our generator polynomial. That means the remaining terms, d plus 1 and d cube plus d square plus 1, those two become part of the parity check polynomial. So the h of d, the parity check polynomial, will be d plus 1 into d cube plus d square plus 1. So when you multiply the two terms, you get d power 4 plus d square plus d plus 1, and that is our parity check polynomial. Again, when you multiply these terms, any terms that repeat two times, they have to be cancelled out. Okay, so after cancelling out, you get the answer as d power 4 plus d square plus d plus 1. That becomes your parity check polynomial, denoted as h of d. Now, once we have the parity check polynomial h of d, we can find the message polynomial from the code word polynomial c of d by this process. So what you do, you multiply the code word polynomial with the parity check polynomial and then divide that product by d power n plus 1. Okay, that is d power 7 plus 1 basically. So when you multiply the code word polynomial with the message polynomial, you get some result. Then you divide that with d power n plus 1, you will get back your message polynomial. So let's do an example for that. So I'm going to take the message corresponding to 0001, right? So correspondingly, the message polynomial is 1 and the code word polynomial is d cube plus d plus 1. Okay, I want to take you back to the previous page so you can see that. So here uh, for 0001, if you can see the pointer, the message polynomial is simply 1 and the code word polynomial is d cube plus d plus 1. I've underlined here on the scanned paper. So the message polynomial I of d is simply 1. The code word polynomial becomes d cube plus d plus 1. Now we want to go back from the code word to the message I of d. From the code word polynomial d cube plus d plus 1, we want to find what is the message polynomial. That is the decoding part. So to do that, we multiply the code word with the parity polynomial h of d and then divide it by d power n plus 1. So we are going to multiply d cube plus d plus 1 with h of d. So let us do that process. So we are going to multiply d cube plus d plus 1 with h of d, which is given by this polynomial. And then you multiply, it's normal multiplication of terms, okay? But the addition part here is modulo 2, so anything that appears 2 times will get cancelled out. If it appears 4 times, again, all the 4 will get cancelled out. So d power 5 appears twice, so it is cancelled. D power 4 appears twice, so it is cancelled. D cube appears twice, so it's cancelled, and so on. So when you cancel out all the terms that occur in pairs, the left out terms after this multiplication is d power 7 plus 1. So that is exactly what is remaining now. And then we divide that by d power n plus 1. So the result of multiplying the code word polynomial and the parity check polynomial is divided by d power n plus 1, in this case d power 7 plus 1. So d power 7 plus 1 divided by d power 7 plus 1 gives us 1. That is our message polynomial, and that is exactly the same polynomial we had previously. For 0001, the message polynomial I of d is equal to 1. So we get back that same 1, the message polynomial, by this decoding process. So if you notice now, our message polynomial I of d is obtained as 1. And then because we know that I of d is of degree 3, so it has d power 3, d power 2, d power 1, and d power 0, that is the last one. So only the d power 0 term is there, so it becomes 0001, right? So I'll do one more example of this by taking another message, and then that will make things clear for you. So let's take the subsequent message from our code words, which is I think 0011 or 0010, I think, right? So what is the polynomial here? D cube plus d square plus d, right? So we'll take that polynomial and multiply with the parity polynomial. So I'm just going to do one more example. So d power 4 plus d square plus d is our code word polynomial, and we are going to multiply that code word polynomial with h of d, which is d power 4 plus d square plus d plus 1. So when you multiply these two terms, you get all these terms, and whatever appears twice, we cancel them out. So d power 6 appears twice, so there's d power 6 here and d power 6 here, so cancel. D power 5 and d power 5 cancel. So after canceling all the terms that occur in pairs, we are left out with d power 8 and d. Okay, so the resulting product of the code word polynomial with the parity polynomial is d power 8 plus d, and we can take the d as a common factor, so it becomes d into d power 7 plus 1. So the numerator part of this process is finished, and we now need to divide that by d power 7 plus 1. So when you divide that by d power 7 plus 1, the d power 7 plus 1 and d power 7 plus 1 in the numerator and denominator will get cancelled out, leaving us only with the d term. Okay, so that means we have only d. The polynomial for I of d is d. So if you go back to the generation part, so if you see here, the polynomial that we have here is d. Okay, I'm just making a pointer. So the polynomial for I of d is d. The corresponding code word is d power 4 plus d square plus d, and when we multiply this with the parity polynomial and divide by d power 7 plus 1, we get back the d that we are looking for, right? That is, we are getting back the message from the code word. So the decoding process is achieved, and then the code the message polynomial that has been decoded, we can map it back to the binary sequence, because we know the message is of length 4. So that means it goes from d power 0 to d power 3, and only the d power 1, that is d term, is present. So only that position is 1, all the others are zeros. So we are now able to get back our message bits. So the encoding process is done by multiplying the message polynomial with the generator polynomial. The decoding is done by multiplying the code word polynomial with the parity polynomial, and then dividing that product by d power n plus 1. In this case, n is 7, d power 7 plus 1. So when you divide it, you get back the polynomial which represents the message bits, and from that polynomial we get back our message bits. Okay, it's a fairly straightforward and a simple process. So the encoding and decoding of cyclic codes is a very easy process. So to summarize, the important things you need to remember here is you need to know to do is, first, how to represent the bits as polynomials, and second thing is, when you multiply the polynomials, you have to remember that the addition terms are modulo 2 addition. That means any term that occurs in pairs has to be cancelled out, because it's like 1 plus 1 is 2 and 2 modulo 2 is 0, right? So remember to cancel it out, and what is left out remain becomes your uh, polynomial for that particular term. Okay, and then you can just, by computing, by knowing what should be the weight or the length of that bit sequence, you can convert the polynomial back to the bit sequence. Okay, so that's to do with cyclic codes, and that also brings us to the end of this chapter on channel capacity and channel codes. Okay, I will stop today's topic. Today we'll be winding up with the error detection and error correction codes. So we have seen three types of codes. Okay, in the beginning of this chapter we talked about the channel capacity. The channel capacity depends on the bandwidth of the channel and the signal to noise ratio of the channel. And then we talked about codes. Okay, the codes that we are talking about, we have been discussing about, is parity codes. And after the parity codes, we discussed about the Hamming code, and in the Hamming code we talked about the 7/4 Hamming code in detail. And then I also talked about what are the different values of n and k that can be used for the Hamming code, right? The Hamming code's n and k values are chosen according to some rule, and that is in the lectures. Okay, that is not available in the notes that I have uploaded, but it's in the lecture videos. So make sure you watch the lecture videos and make sure you make your own notes for that. Okay, it's clearly explained that n should be 2 power m minus 1 and k should be 2 power m minus 1, right? So those rules are all given in my previous lecture videos, which you can see and try to make the notes of it. Okay, it's clearly explained there. And then we also talked about the 6-3 linear code, which is not a Hamming code, and I also talked about the properties of the parity matrix. If you remember, the parity matrix, the P matrix in the G matrix, it should follow some rules. That means it should not have all zeros, it should not be repeated, any row should not be repeated, and each row should have at least 2 ones. Okay, those are the 3 criteria that we should follow to make our parity matrix. The first part of the generator matrix is an identity matrix. The second part of the generator matrix is the parity matrix. And we talked about the properties of the rows of the parity matrix, that they should not be all zeros, they should have at least 2 ones, and they should not be repeated, right? And today we have talked about the cyclic codes, the polynomial representation of cyclic codes, the generator polynomial for cyclic codes, the parity check polynomial for cyclic code, and the encoding and decoding procedure for cyclic codes. Okay, so that brings us to the end of this chapter. In the next lecture, I will start the new chapter, which is digital modulation. So maybe in another 2 lectures, or maximum 3 lectures, we will be finishing off the topic. So by next week, we will be finishing off. We have another this week, and follow after this week, we have 2 more weeks of classes. But I will finish off everything in the next week itself. So the last week is available for any discussion that you might have. Okay, to clear your doubts and to clear your questions and what. So we will have time for that, and that will bring us to the end of the course. Okay, but for today, this chapter is finished. Of the chapter of error correction codes is finished. In the next lecture, I'll be starting digital modulation. Okay, we will talk about that in the next lecture. For today, if you have any questions regarding today's topic, you are now free to ask your questions. Okay, I'm waiting for your questions, guys. And just a quick reminder, those who have not yet submitted the assignment, well, I think the deadline is today night, so upload it on the assignment section. Today's notes, it will be uploaded. Yes, the scanned pages on today's notes, right? The scanned papers that you saw in the slides today, I will upload them on Blackboard. Okay, and regarding the video is also recorded, so you can download the video directly from Blackboard. I don't need to upload. I think this recording is available for you to access, so you can also download this recording and you can watch the recording again as many times as you want. If you have any doubts, you can also contact me, and or you can ask me in the next lecture or in the last week also. So you feel free to ask your questions, right? How did you choose the generator polynomial? Right, the generator polynomial is a factor of d power n plus 1. So you have to do the factorization. So d power n plus 1 for the 7, 4, it is d power 7 plus 1. So you divide d power 7 plus 1 by d plus 1, you will get some term with d power 3, d power 6. Again, divided by d power 3, you will get the factors. Okay, it is long division basically. All right, I can't be covering long division here. You are expected to know long division, right? So by using long division, you get these factors, and from the long division, you take the factors which is of degree n minus k. In this case, 7 minus 4 is 3. So d power 7 plus 1 has factors d plus 1, d power 3 plus d plus 1, d power 3 plus d square plus 1. So we can choose either the first d power 3 term or the second term which has d power 3, because it is required that the generator polynomial is of degree n minus k, which is 7 minus 4 in this case. How many lectures we have? We have lectures till the last day, okay? The last quiz mark is not available. You will see it very soon. You will see your last quiz marks maybe today or tomorrow, inshallah. Okay, guys, any other questions that you have, you can ask me now. And again, I was talking about the assignment. Okay, those who have not yet submitted the assignment, please remember when you upload the assignment, write your university ID number in the assignment, or at least name your assignment file with your ID number so I can know whose assignment it is. How many quiz? Already you have done 4 quizzes, right? You have done 2 quizzes for 5 marks, and you have done 2 quizzes for 10 marks and 10 marks, right? So out of the 5 marks, out of the 2 quizzes for 5 marks, I will take the best one. Out of the 2 quizzes for 10 marks, again I will take the best one of the 2. And then you have the 2 short tests. The short test, the first one is on Tuesday, the second one is next week. I will make announcement for that. For the first one and the second one, a short test, I will take the best of the 2, okay, the one best out of the 2. So that will be the short test. And then I will add one more quiz next week for 5 marks, and that will be counted. The last quiz will be counted, okay? Can you explain how the questions will be like? For which one? You mean for the short test? Yes, for the short test. Okay. For the short test, it is like the quiz, multiple choice, and maybe with some calculations also. But it will be simple calculations, like find the sampling frequency, or find the number of quantization levels, find the step size, or multiple choice, right? Like you have been doing the quizzes, similar to the quizzes, but more questions and more marks and more time. Okay, the quizzes usually you do 10 minutes or 15-minute quizzes, right? Uh, but the short test will be for maybe like 30 minutes, and the daraja for the short test is 25 marks. So you will have maybe anything between 15 to 20 questions, and the time will be approximately 25 to 30 minutes. And after the 2 short tests, I will take the best one. Okay, so far you have done 4 quizzes. What is that? 15. Well, I can't give too many quizzes. Okay, I've already given you 4. Out of the 4, I'm taking the one best. There are 2 quizzes for 5 marks. Okay, out of the 2 quizzes for 5 marks, I'm taking the best one. Out of the 2 quizzes for 10 marks, I'm taking the best one. Out of the 2 short tests, I'm taking the best one. So you have a lot of chances, a lot of benefits. Okay, I can't keep adding more and more and more quizzes. Okay, so you had 2 quizzes for 5 marks, I am taking the best one. 2 quizzes for 10 marks, Wahid Ahsan, the best one. 2 short tests, Wahid Ahsan, that is the best one. Okay, and then you have one more quiz of 5 marks which I will give, and this will be the final quiz, and it is a compulsory quiz. There is no best one for this, so make sure you do it properly. Okay, the last quiz for 5 marks. For those who have already submitted without writing the ID, leave it. Okay, if you have submitted from the assignments, no problem. Those who are yet to submit, please write your ID number as your file name and upload it. So that will make it easy for me. Otherwise, it is taking me too much time to search whose assignment is this, because you are not writing your ID number even in the assignment paper. So it is becoming difficult to track whose assignment it is. So please write your assignment. So write your ID number in the file name. There is one more of 5 marks quiz which is next week. Okay, so please don't keep asking me more quizzes. I can't keep giving more quizzes because we don't have time for it. Okay, you have 2 more short tests and you have 1 more quiz, and that's it. Okay, your assignment will be finished today. You have two short tests. I will take the best one, and I will give you one more quiz next week, and that's it. Okay? Because I don't think we'll have the time to do more things. That's the problem. In the last week, we will see if there is time, if we can do something, but I don't think we are going to have the time for it. So it will be as my announcement. I have announced on Blackboard what all is remaining in your assessments. So we will do according to that. Okay. So any other questions, guys? All right, guys. Okay, we'll meet again in the next lecture. Okay, take care.